Greetings and welcome to this presentation on advanced topics and research methods. The information provided here is going to closely parallel much of the information provided in Aronson Chapter 4, which is a pretty dense piece. And so I highly recommend listening to this first to get the big picture, hit some of the highlights, and then be able to skim judiciously that dense chapter, fill in some of the details if you wish, but being able to keep the important concepts in mind as you do so. Also, another objective of this is to give us practice in critically thinking about causality and being able to anticipate and address potential objections to our research. So how do we rule out plausible causal alternative hypotheses in a way that's smart and anticipates any critiques in the future of our work? So when you go to the conference here and somebody asks you a question, you've already anticipated it and been able to use design controls to rule it out. So to illustrate this, I want to talk about a study that's very famous in social psychology, and it was conducted on this bridge here in Canada. It's a suspension bridge that's pretty high in the air. It's the Capilano Bridge. I've never been there, but at the time of this recording, at least, but some of you may have gone across it. And basically what the researchers had is a theory regarding unexplained physiological arousal. And this is a pretty sophisticated theory because they said that two things have to happen before the effect would be seen. First, the physiological arousal is experienced, but it's not consciously labeled. So it's like it's in system 1, but not at system 2. Remember, physiological arousal produces symptoms like increased heart rate and breathing. You feel more alert. And then you are presented with some kind of external cue. So someone is going to behave in a certain way to and show some kind of emotion or give you some kind of cue, and I'll get into that in a second. And then after that, so you have this unexplained arousal plus this cue, and that is going to yield an emotion. You're going to have an emotion that will be in accordance with the cue. So to clarify, if you don't have this unexplained physiological arousal and you are presented with the cue, it won't work. So those two things have to be come together, the arousal and the cue. Okay, so for example, walking across a high bridge, so experiencing some physiological arousal from this, plus you're presented with an attractive female. If you are a straight male, presuming, then you will experience sexual attraction toward that person. Now, let me note again here that the arousal has to be unexplained, so we can't get into system 2 and actually label it as fear. So the person has to be thinking about something else, but they're still physiologically aroused when presented with the cue, i.e. attractive lady. So the researchers back in the 70s or 80s, I don't remember, but it was some time back, they went to this bridge and they caught some male potential participants, first of all before they crossed this high bridge, and then some different ones after they crossed. So I don't believe it was the same people. And they first asked the males who were coming up to the bridge, hey, can you participate in a research study? This attractive lady asking, she had a clipboard. I think she was like asking for tourist information. I forgot what the cover story was, but didn't want them to suspect. And then she said, if you need want more information about the findings of our study, here's my number. And she gave them her card to her personal number. So that it was clear to them that it was her personal number, that they would be talking with her specifically. And that was the DV. Isn't that clever? That they used how many callbacks she got as a sign of their interest in her. So that was the control condition. The experimental condition is assuming that these men had just crossed the bridge, they would be in a level of physiological arousal to some degree. And then the female researcher was there with her clipboard asking them to participate in a study, and then she gave them her number. And the group who called her the most were the ones who had just crossed the bridge. So the researchers took this as evidence that was consistent with their theory. Now, there's a very famous study that is talked about in Aronson in some detail by Schachter and Singer. And they did a study, I think in the 60s or 70s, where they wanted to test this theory of unexplained arousal as well, but they wanted to do it in a more controlled setting than the bridge. So, and a little more invasive, as you'll see, because they decided to inject epinephrine into some participants to induce physiological arousal. Epinephrine will make your heart rate elevate slightly. I've never had an EpiPen shot or whatever, but I'm presuming it's akin to coffee, except more to a higher degree. And so you become very alert and maybe jumpy, fidgety, etc. Now for IV number 2, they decided to have an external cue. So remember, we have to have the arousal and then the cue. And so the cue, they decided they would introduce a confederate who would either act happy or angry in the participant's presence. And so that was independent variable 2. Now the DV was the emotion that the participant reported on a scale, I think it was some kind of self-report measure. So remember, the theory again is injected by the epinephrine, so they would feel arousal, but they probably couldn't explain it, which I'll get into in a second. And then they would be in the presence of someone who would give them a cue, and then the ones who had the epinephrine would fall in line with whatever the confederate did and feel that same emotion. Okay, so the experimental group, what did that entail? Well, first they were all injected with this epinephrine, but provided no explanation of what to expect. So here's a shot, and we're not going to tell you why. You know what, they may have given some explanation, but I don't think they did, in this group at least. So again, when these people were injected, then they were exposed to this cue by the confederate, and the expected behavior is that they would feel the same way as the confederate acted. Now let's turn our attention to dealing with some plausible alternative explanations. So to get on the same page, we have an experimental group that was injected with epinephrine, introduced to a confederate, and their behavior, or their feelings coincided with whatever the confederate did. And then we have a group that was not injected, the control group. And that control group did not get an injection, and they were exposed to the confederate, and we would not expect the confederate would have any sway on their feelings. However, let's say that just getting stuck with a needle creates enough arousal to, to mimic the effect that we would want to see. So it could be that we have committed a type 1 error. It's not the unexplained arousal, it's just any arousal from getting stuck with a needle. And so in order to rule out that specific explanation, we are going to have a control group in which people are injected with a needle, but it's a saline solution or some kind of placebo. So it is not supposed to have the effects of epinephrine whatsoever. And that way we can see if the epinephrine or the arousal explains above and beyond any arousal that is just due to being stuck with a needle, which we would assume would be less of an arousal than the actual epinephrine having an effect inside the body. So we expect that there will be an arousal with the epinephrine that is more than simply being stuck with a needle. And in order to test that, we are going to make another control group. So we have, again, a control group with no sticking in the needle, a control group with a placebo needle, and then the experimental group with the full manipulation, the epinephrine. Okay, so we're going to rule out this type 1 explanation that being stuck with a needle caused the effect. It wasn't the arousal from the epinephrine. So that's what we're going to rule out with this group. Okay, there's another potential objection, and that is that the effect has to be unexplained. And so maybe being stuck with a needle is enough for people to label it, the arousal as what it is, and so we won't see the effect. And so how do we rule out this issue? Well, we'll make another control group, and this will be an injection group, so an epinephrine group, And so those people who are injected with the epinephrine will be told that they will experience all the symptoms that are in line with epinephrine. So they'll be shaky and their heart rate will increase, etc. And so again, the purpose of this group is to test the theory that this arousal has to be unexplained in order for somebody to look to the confederate and infer their emotion from the confederate. And so if our theory is correct, what kind of pattern of findings would we expect to see? Well, we would expect that this group that's provided the explanation will not be swayed by the confederate when they are presented with the confederate's behavior. So they will not infer their emotion, but the ones who were injected with the epinephrine who didn't get the explanation, they will still change their emotion based on what the confederate does. So again, here what we're doing is we are anticipating a potential objection or an alternative explanation that could be going on. And we want to make sure that we are testing our theory as precisely as we can, and granted, this is quite a complex theory because you have two things that have to happen for the outcome to occur. So in this case, we are ruling out the explanation, or the alternative causal hypothesis that you have to have this arousal be unexplained in order to see the effect. And it could be that people who were injected with the salt, the saline solution, and the people who were injected with the epinephrine both attributed their symptoms just to the stick of the needle. And so they were able to do that consciously, and then we wouldn't see an effect. So basically, this is going to keep us from committing a type 2 error. We don't want to see nothing when there is something to observe. Okay, finally, this is a little bit of a crazy one, but let's say we go to a conference, we're presenting our findings, and we found the effect that we wanted to see, and someone in the audience says, look, it's not the information that you gave them that was accurate necessarily. It could be that we would have seen the same effect, that is, people did not infer their emotion from the confederate in that group where we explained and gave them an accurate forecast of what they would feel physiologically, but rather it's any information that you give them. So it doesn't have to be accurate information, it can be any information you give them. So you can give them any explanation, even if it's inaccurate, that they'll experience this other thing, and they will still behave the same way as they did in the accuracy condition. Accuracy control group, I should say. So what do we do with this? Well, if we have resources to do this, we can do the study again, and we can add another group, and we'll provide inaccurate information to that group. So we'll tell them that, well, I'm going to inject you with this, and it will really be epinephrine again. But you are going to have numb feet and a headache or something else, something that epinephrine does not induce. So we're going to tell them misleading information, and then we're going to expose them to the confederate and see what they do. So let me think for a second. If the person, in the inaccurate condition, if they do not respond to the confederate in the way that we expect and mirror that confederate's emotion, then we know that participants will use any reason to explain their arousal, even if it's inaccurate. And so we would have to go back and revise our theory at that point. However, if these inaccurate participants that were given inaccurate information actually do infer from the confederate, then we'll know that they weren't listening to the inaccurate information, and they were still had no explanation for the way they felt. So they had the shakiness and the epinephrine symptoms. And those were unexplained still because we gave them inaccurate information. We told them they'd experience something else that they're not experiencing. And then, so that unexplained arousal will cause them to mirror the confederates' behavior. So we can rule that out in that sense. Okay, so in closing, before I move on to other topics here, Anticipating potential critiques of our studies and alternative causal explanations is really essential. Will it lead to a type 1 or type 2 error? It's important for when you are working with clients or writing up your dissertation and your committee has questions. It's really helpful to have the capacity to anticipate their concerns and be able to address them if they come up. We're going to talk more about this in Program Eval. Program Eval is going to be, well, at least a portion of it's dedicated to understanding alternative causal explanations and being able to, talk about those or articulate those with clients and in class and in your write-up of your project. So I'll look forward to that. But this is kind of a preview for that. And so as you're reading through Aronson and reading through some of the studies, take careful note of when the authors start to go into explaining away alternative causal explanations in a good way or not so good way, it doesn't matter. But when you see the authors doing that, you can at least, it registers in System 2 that this is what's happening. They're trying to anticipate any critics' objections to what they're doing. And that's a sign of good writing, actually, is to be able to, think about what could be said that is not in line with what you're saying and head off those objections, so to speak. So that's the whole goal. Moving along, advanced concepts associated with experimental design. So when we're doing a study, it doesn't even necessarily have to be experimental, but when we're doing any kind of empirical investigation, what are some of the decision points and also just the ways of thinking about research? So those are some things I'm going to talk about here, kind of a miscellaneous set of topics. Okay, so the first one, systematic versus random error. Okay, so systematic versus random variance. So whenever we're attempting to establish any kind of causal relationship between two variables, we want to parse out the signal from the noise. So the signal is the systematic variance, predictable variance, that is due in the DV, so whatever your outcome variable is of interest, that is caused by your IV or your manipulation. So usually when you do stats, you get a certain percentage of variance in the DV that is explained by your manipulation. And that's what we want to know. That's called the signal. That's important. We want it to be strong, or as strong as possible at least. So the error, on the other hand, is the residual variance in the DV that's not explained by our manipulation. It's variance in which we're not interested. So it's important to think about when we introduce a manipulation to people, we want it to have as big an effect as possible so we can detect it out of all the noise in the DV. And again, noise is variance in the DV we're not interested in. We're only interested in the part of the DV that's being moved, quote unquote, by the IV. So what's being moved by the IV? This is why clients will pay you the big bucks, is because they want to know how accurately, I should say, can we predict the DV based on particular IVs of interest. And those may be characteristics of people, like your personality, selection test information. So you have people take an assessment before they get hired. And we want that to predict the DV, which is job performance later, because that's going to be very important. That's why you're hired a lot of times. And so it's important to think in these terms. So Aronson talks about what mutes that signal so we can't detect it as easily. And so he talks about things like if you have a very diverse sample in terms of both demographic characteristics and other things like life experience, different skills, different things that you've been through in your life, all of that creates noise. It creates other things that are impacting the DV that are outside of the predictor variables we care about, or the manipulation, the intervention, etc., that we want to impact that DV. And so all of these extraneous variables, we call them, create error variance that we have to cut through with our manipulation. If we have participants come to the lab, we need to have a strong manipulation that impacts them all uniformly, and it's potent in the sense that it affects them strongly and uniformly. So they'll hopefully respond to the DV in the way that we want. And it's the same thing when you think about interventions in orgs. We want an intervention that is potent and that affects everybody, lands on everybody as equally as possible, so that we can cut through the noise of all the other variables. Again, different personalities, skill levels of people, different ways they think. If we can create an intervention that's that effective, we hope to be able to cut through that noise. So to the extent that we have a very diverse sample, and diversity can mean many different things, which we'll go over later in this quarter, but if we have a very diverse sample, that means that we have to have very strong manipulation to cut through all that noise. So if we find an effect, regardless of a diverse sample, it's a reason to rejoice. Now, systematic variance is a little bit different. And I have a couple examples of this. Systematic variance is error that is predictable. So some people don't even like to use error. In fact, systematic error is kind of a misnomer. So just for nomenclature, just noting nomenclature here, some people don't like to use the term systematic error. They would like to use error as random variance rather than anyway, they don't like to use the word systematic error. They would rather use systematic variance. So anyway, that's just a quick side note. Okay, so systematic variance is different than error variance because even though it's variance that we don't care about, it's not the manipulation. So it is variance that is not relevant to what we want to look at. It is, what it can do is mimic our manipulation or intervention and cause us to make a type 1 error sometimes. So, for example, I have two examples of this. First, a confederate may subtly behave differently to participants in the manipulation group, causing them to respond in ways that are consistent with the researcher's hypothesis and confirms it for the researcher. So the researcher thinks, yay, my theory worked, but in reality, the confederate was behaving differently toward people in the experimental group versus the control group. And that is called systematic variance, and it is error in the sense that we're not interested in it, and it's going to make us make an inferential error in terms of causality, which is bad. So it leads to a type 1 error in this case because the confederate was behaving systematically different between the control and the manipulation or experimental groups. So that's an issue there. Now, maybe the confederate for some reason did not want the researcher to confirm his or her hypothesis. So they decided to behave systematically differently in the other direction. With the control group, they behaved in such a way that would nullify the researcher's hypothesis. And this is also systematic variance, but it leads us to commit a type 2 error this time. That is, we don't see an effect when there really was one. And that is because the confederate behaved systematically differently. Systematic just means it's predictable error. That's all it means. So error that can be predicted. So because the confederate acted consistently in one condition versus and not in the other, that is systematic or predictable error. Or bias. Systematic error is also known as bias in the field. Now, if the confederate did random things, didn't matter which group they were in, they just did random weird stuff that made the participants respond weirdly, but they did it equally across both groups, then that is true error, random error, and that just creates more noise that when we can't find an effect, basically. So noise makes it more difficult to detect the signal, it mutes our effect, and creates a situation of type 2 error. So think about the difference between systematic bias or systematic variance that produces a type 1 error, usually, or could be a type 2 as well. But then random variance always causes us to commit a type 2 error. So separate those two things. Random error always mutes our effect. Systematic bias, on the other hand, can go either way. Now, just to clarify, I'm going to give you another example. Remember, Kahneman talks about, in one of those chapters, I think it's chapter 7, about eyewitnesses to some event. And so if the police officer is coming to a scene of some kind of accident or crime, it says that Kahneman says that person will want to make sure the witnesses don't talk to each other, because once they talk to each other, they start to remember things similarly, even though that's not the case, because they influence each other unduly. And so they start to come to a false consensus. And this is systematic error, because they're influencing each other and starting to agree more with each other, when in reality, if they had stayed separate and each told from their independent perspectives what happened, the police officer is going to get a more accurate account of what happened. And Kahneman calls this independent observations. That means that each person did not speak to the other, so they weren't influenced by each other, and they were independent, and each told their story without any of bias from the other witnesses. So it's important to have independent observations and average those together to get the best idea of what happened. So again, we don't want many witnesses who have come to consensus. Oops. We don't want many witnesses who've come to consensus when we're trying to get at accuracy. And we don't want just one independent observation either, because that person's prone to their own errors, and we have no one to balance them out. The ideal, when we're getting at accuracy or rating a target or trying to figure out what happened at a crime scene, accident scene, whatever the case may be, we want multiple independent observations that are averaged together. And that's going to be a concept that comes up later in this class and in other classes as well. So again, the two undesirable options and the desirable one. We do not want many eyewitnesses or raters who have come to a false consensus and influenced each other. Neither do we want one independent observation, just one person rating. We want many independent observations. That's the goal. Okay, moving along, let's talk about properly specified models. So a properly specified model means that we have a theory regarding how certain variables interrelate with one another, and the extent to which that theory maps on to how those variables are interrelating in reality, that means our model is properly specified. Okay, so how well does our theory comport with reality, basically? So I'm going to give you a couple examples of how people misspecify models, and I think these are most common. The first one is the relationship between an IV and a DV. Is it linear or curvilinear? So here we have a positive linear relationship between two variables. Maybe meditation is on the x-axis, and then stress. I'm sorry, that's probably not the best example. That would be a better example for this. So let's take this negative association first. We would have mindfulness or meditation on the x-axis, and then we would have stress level, such that as we do more meditation and mindfulness, our stress level decreases. We have this negative association. For positive, this could be as our job performance increases, our satisfaction will also increase, because we'll be demonstrating our competence. And then we have this curvilinear relationship. And so curvilinear relationships are when we have a sweet spot, so to speak. So we have the highest level of performance at a moderate level of stress, for example. So at very low levels of stress, we're not very motivated, and so we're just not going to do much. And at very high levels, we start to shut down. That's not good either. But at some moderate level, it's pretty good. We can perform pretty well at a sweet spot, so to speak, of stress or alertness, if you will. Also, we can have direction of causality. That needs to be properly specified. So we need to be able to have an accurate idea if X causes Y in reality, or if Y is causing X, or vice versa. And I already talked about this with the illustration of job satisfaction and performance, which comes first. And then finally, we have to have moderation and mediation properly modeled. So especially the moderation, this is a big deal, because if we claim that stress at work impacts turnover, but it does so differently for men and for women, but we don't say that. We don't say that gender moderates that relationship between stress and turnover, then people will be making wrong decisions about other people's welfare, because we haven't specified that this relationship only holds under certain conditions. And so specifying the moderators is really important. Okay, so here's another relationship, and this was talked about in Aronson as well, this curvilinear relationship between physiological arousal and performance. And for difficult tasks and easy tasks, it looks a little bit different. So I'll let you read about that in the slide here and also in Aronson. But I just want to say that curvilinear relationships are really neglected in our sciences, and that's because I think they're difficult to test. We have to have maximum variability on the IV, for example, in order to see that curve come out. Otherwise, it just looks linear a lot of times. And we don't want to tell people that more of something is always going to be better when it's not. More arousal does not always help us. And low amounts don't help us either. In this case, it seems like moderate levels of arousal is where what we want to shoot for. For difficult tasks is going to be lower because we're just less apt at those tasks. And then for easy tasks, we can get by with more arousal. But even with easy tasks, if we become too aroused and too stressed out, so to speak, then we're going to see that sharp decline in performance. So I would say that most or many of our relationships that we in real life that we see between two variables aren't the simple linear, but that's, I think, our default is we assume this they're linear, especially positive linear. We kind of make that default assumption, maybe with system 1. And when in reality there are moderators affecting it. It might be curvilinear, nonlinear, and so those are some things to think about. Okay, let's talk about matching. Matching is when we want to ensure that our experimental group and our control group are similar on all possible variables except for the variable of interest that we care about. And so twin studies have been done many times, and twins make an excellent match for a matching study. They make excellent participants because you can take a twin and they're very similar to the other twin, and so if you introduce a manipulation on one versus the other, you can get a clearer picture of whether that intervention is working or that IV is working because the noise is cut down. Remember, any variables that differ, that make these people differ, are going to create noise. All right, so let's say you're overseeing an intervention at Starbucks, and this intervention is supposed to be implemented at select locations, and it's intended to positively impact sales. So it doesn't really matter what exactly this intervention is. Just imagine that some kind of positive thing that they're employing in order to, up their sales. So we would want stores who are implementing the intervention to be as similar to stores who aren't implementing the intervention, so we can see clearly that intervention's effect without without having noise, random error, but random error might be always the case in this particular situation. I mean, I should say we can't totally get rid of it. But we certainly don't want systematic variance. So we don't want the stores who are implementing the intervention to be systematically different in some way than those that are not. So I took the variable of geographic location. And so geographic location matters to sales, perhaps, because stores that are in the same geographic location may be subject to similar variables in the environment, the local economy, events that happen in that area that impact Starbucks business. And so what we wouldn't want is all the stores that are implementing this intervention in one area and then we're comparing them to stores in another area. It would be best to match them such that same geographical area, we have one store that has the intervention going and one that doesn't, such that stores are matched on geography and local economy variables so that those variables aren't creating confounds and making them systematically different in some way that is a result of variables that aren't the intervention. So we don't want to create a situation where we make a wrong inference. Okay, so match the stores by geographical area. So the key to using matching is to think of the variable that could be a potential confound. And a confound again means that it is a variable that's impacting your DV that is not your intervention, but that mimics the effect of your intervention, causing you to make a type 1 error of inference. You can also implement this technique with, I used the illustration of stores, but you could do it with people as well. If you only have a few people who are taking the intervention and who are in the control group, and your boss tells you you can randomly assign, but if you randomly assign, that means you could end up with unequal groups even with random assignment if you have just a few. So what you can do is take the variable that you believe will be the confound, such as personality of the people, maybe conscientiousness, and you can measure them all in conscientiousness and then take the top 2 scores on conscientiousness and randomly assign 1 to the intervention and 1 to the control. Maybe the control group will get the intervention next year. So it's not like they're being deprived of something. And then you take the next 2 scores on conscientiousness. They're very similar. And you randomly assign 1 of them to the intervention and the other to the control. So matching can be done several different ways. The goal is not to know all of the exact different ways, but just understand why we match philosophically. What is the reason for why we want to match? And then have one example. That's my goal for you, is to have just one example like the Starbucks store example. Okay, attrition. Attrition happens when people exit the study before it's finished, and this is particularly a problem with longitudinal research because people move away from your study or they just become lazy, don't want to fill out all the measures, and so they drop off. Now, random attrition means that nothing is predicting who will drop out. The dropout is the same across both conditions, intervention and control, IV and control. And it's totally unpredictable. So the groups don't differ in terms of who leaves the study and why they're leaving. It's all random. So if it is truly random attrition is no big deal for your study. It just cuts back on your n size, which is a pain. But if it's truly random, it's not going to impact your inferences. The issue is we never really know if it's random because the people who drop out, it may look random, like, the people who drop out don't look any different than the people in the control who are dropping out. But at least on the outside, they don't look different, but they may have internal attributes that are different that you don't know about. Okay, so it's one of those things. Random attrition is not a big deal, but we never really know if it's random. Which is why, if you have attrition, you should try to ask the people who leave why they're leaving. One good way to go to try to get at that. Differential attrition is when the groups do differ in terms of the number and types of people who leave. So for example, if more women drop out of your intervention group than men are, then that's a sign that something is going on and you could make internal validity inference errors in that case. So it's like this selection threat to internal validity where people volunteer for your study, they're different, or their intervention are different in some way from people who don't go into the intervention and they're in the control. It's basically like that, but in reverse. So certain people stay and they differ systematically from people who leave. And so that's explaining your results and not actually the intervention. So it's usually a type 1 error issue. Not always though, but you can think of attrition as potentially a type 1. Okay, so I think actually I give you an example of a type 2. So it's a little bit of an anomaly, but it could definitely happen. And this is a welfare to work program, and it's, let's say, an extensive one that, is prone to attrition. It's 3 months long. Maybe it's a weekly sessions or bi-weekly sessions where they come in and get some job skills. And the results indicate after that the program didn't work as intended, but you notice that people were dropping out of the intervention group. So you get to the end and they're not statistically different. Now, this could be solely due to lack of n size. If enough people left that intervention group, then you're left with 10 people in the intervention group and you have 50 in the control. Just the n discrepancy alone, that subgroup n size discrepancy, could cause a type 2 error. But let's say you have thousands of people, so it's not really that issue with n size, but it could be an internal validity issue where you concluded the program didn't work, but the people who left the intervention actually were leaving because they got jobs. So the intervention was working, and the people who were in the intervention group were more likely to get jobs, and that's why they were leaving. But if you didn't track why those people were leaving, then you would conclude your program was crap and you'd scrap it. So this matters. Like when you're working with clients, you have to be able to think these things through, and this is one example of a quiz question or an exam question I could give you where you would have to think through, okay, what are some potential reasons for why this happened? So was this a type 2 error versus type 1? And I think you could go from there. Once you determine it's a type 2, then what are the potential reasons for type 2? So you would explore as a consultant, again, why people were leaving. Were they leaving just because they were bored? Were they feeling like the people who weren't as conscientious can't stick it out for 3 months maybe? And if that's the case, then you might see a type 1 error happening where the people who are very conscientious stay through the whole thing, and that's good, and the people who are in the control drop out maybe, or something like that, because they're not having, the people drop out who are unconscientious in the intervention group because it's really tough. Let's say the program is long and difficult, and those who don't have a lot of conscientiousness are like, ugh, I'm going to leave. And so that leaves only the conscientious people in the intervention group. And those people will have better outcomes just because they're conscientious, not because the intervention actually had an effect. So that's an example of attrition causing a type 1 and not type 2. So I think it's really fascinating. This is just good practice to help you think like a researcher, to be like a detective. All right, in summary, let's go over just what are some of the takeaways from all of this. When attempting to test a causal relationship between any two things, think about how would my results look if my theory was correct. So what pattern of results would we expect to see? So this group should be higher than this group or lower than this group, etc. What factors could possibly cause type 1 error? Okay, usually these come in the form of confounds. Confounds are things that confuse us. If you've ever heard the term like, I'm so confounded by this problem. Confounded means that you're confused, and confounds make us confused between the following options. So you're confused as to whether it was the intervention or the manipulation that caused the effect, or was it something else that caused it? People were just more conscientious in the group that had the intervention, or the geographical area impacted the sales, not the intervention. So those are the kind of things. And can you anticipate any reviewer's critique of your study if you found what you were expecting to find? So you're all confident in presenting your data at a conference, and if you find what you expected to find, it's a great thing, but just know that that could be an error. It could be something else that was causing what you thought. And so it's good to be able to anticipate that and see what you can do at the design stage to rule it out, or capture some control variables, which we'll learn more about in program evaluation, to try to rule those out as well. What factors could cause type 2 error? So usually those are construct or stack conclusion validity matters. So if your participants are not responding uniformly to your manipulation in your manipulation group, that causes error, and it's just harder to find results. Let's say your experimental group, half of your participants respond in one way to your manipulation and the other half are responding the other way. And you're like, oh, why is that? Maybe the women will respond one way and the men another, just to keep it simple. And when you have a group split like that, your experimental group split and then your control group, it's really like you have 3 groups. And if you aggregate those 2 groups together that are responding differently, you have all kinds of noise and you won't find an effect. So what's the solution to that? Well, the solution is to try to make a manipulation that's strong enough such that everyone responds similarly. Or you can model the effect of that moderator. So if men and women are responding differently, then use gender as a moderator and make your model more properly specified by including that. Sometimes you're not manipulating what you believe you're manipulating, or you're manipulating three things together rather than just one construct. That is a typical issue, especially in social psych research. One of my social psych friends was telling me this just the other day, saying that if you're trying to manipulate just one variable, you're probably doing it unsuccessfully. And this is something that even the experts haven't truly figured out. Like, how do I manipulate self-efficacy but leaving self-esteem constant? How do I do that? Because they're so tied together, especially for many of us. When we are not doing well at a task, we kind of feel bad about ourselves, at least to some degree, right? So how can I manipulate self-efficacy while keeping self-esteem constant? It's always a struggle, and it's not a perfect science for sure. Range restriction. I talked about this in the prior screencasts, but range restriction on any variable will mute any effects. So when people are all responding highly or low to certain survey, that's going to impact your likelihood of finding the effect that's really there. So any range restriction is not good. If you have gender as a moderator, this goes for categorical variables as well as continuous variables. If gender is a moderator and you have 90 men in your sample and 10 women, you're not going to find that as a moderator because you have no variability on gender. Full variability or max variability on gender would be a 50-50 proportion, 50% men and 50% women. Otherwise, you're probably not going to find the effect. So if you propose a moderation in your study and those subgroups are that unequal, you're probably not going to see that moderator come out. So, and it's not because the moderation didn't exist. In reality, it's simply due to your sample and that you didn't have equal number of men versus women. And finally, the relationship could be improperly modeled. Again, you're missing a moderator or you're not accounting for a curvilinear relationship. You're concluding that more is always better or something like that. I like to use the example of, I think I said in class a while back, but glasses of wine. If one glass of wine is good, then 10 must be better, right? And that's an example of inferring a linear relationship when in reality you're going to have diminishing returns at some point after your third, fourth, and fifth, and so on. Glass of wine in one sitting, you will experience less enjoyment, less health in that case. And so that's a good example of, I think, a curvilinear relationship that is an upside down U-shape, which a lot of them are, where we have at moderate levels, just a couple glasses, you have your max enjoyment, and then depending on who you are, and after that it's going to start to take a steep dive downward, I should say. Anyway, well, that is all for today. Thank you for your attention. This is a lot of information, but as you continue to work with the nomenclature, think through these concepts, and especially talking out loud using this language is going to embed the concepts deeper and help you to build familiarity so that the comfort level increases with talking through some of these matters. Take care, and I will see you in class.